Today we will be starting with the sixth module of computer system architecture, and in this module we are going to see some of the various multi-threaded computers as well as data flow computers and how their architecture is being built. So moving quickly through the contents of this particular module, you can see we have five major topics. First one is about some techniques that you can adopt for hiding the actual latency that may occur while a parallel computer is under execution. Then about something called the problems of asynchrony. Then we'll have a discussion on multiple context processors or processors which are able to handle multiple contexts of executions at the same time. Then we'll discuss about fine-grained parallelism, and finally hybrid and data flow computers. So let's start with the first topic, which is the latency hiding techniques. So as an introduction, when we start with this particular module, we have to define the concept of multithreading. So as we have already discussed multithreading in the courses of operating systems, or even when you were learning the Java programming. Here, when you talk about multithreading in the case of a computer architecture, it is just mentioning that capability of the execution unit, to be precise, the processing unit. It may be a single core processor or a multiple core processor, and the ability of the processor to execute multiple processes or tiny units of processes concurrently or at the same time is called multithreading. Okay, and multithreading always requires the support of operating system, because it is the job of the operating system to switch between the executions, to interleave the executions, and also to schedule the execution. So that ability of a processor, it may be a single core or a multi-core processor, the ability of a processor to execute multiple processes, multiple distinct processes, or multiple subtasks of the same processes in a given time, in the same time, is called multithreading. And this will be done with the support of operating system. So, as I told before, when we are talking about the parallel processors, obviously, whether if you are going for a pipeline or if you are going for a hardware parallelism, it is sure that there may be chances of a latency. Latency, the term latency here talks about the delay that may occur between giving the input into the system and to finally receive the output from the system. So this latency may occur in the case of, even if in the case of a parallel computer, even if it is going to handle multiple instructions at the same time, there are chances that there will be a latency. So it is always better to not let the end user know about this particular latency that is being occurring in the machine. So what you can do is that you can reorder or you can reschedule the executions or the order of the order by which the processes are getting executed, and thus you can make the user unaware of the latency that is actually happening in the underlying architecture. So this mechanism is called latency hiding mechanism. So latency hiding technique. So as I said, what we are trying to use is that we are trying to reduce or hide. If you can reduce, then it is very good. If it is not able to reduce the latency, then you have to hide the latency from the user, especially when you have memory access. Okay, so in distributed shared memory machine, access to the remote memory is likely to be slow, and you have to either reduce it by using some caching or other mechanisms, or you can hide it by reordering the order of executions, or allocating the resources to some other process and making this processor keeping on alive. Okay, so latency hiding is a technique that hides the time consumed in the micro task by communication and remote memory. So there are three techniques or three mechanisms which are used in the case of a parallel processor. First one is called something called prefetching, which is we have to keep some extra memory, and you will be prefetching the required data, and then you will be executing the process or the micro task, even the threads. So that is the first mechanism. Second mechanism is that all of the distributed memory units will have something called the cache, which will be coherent to each other. So they will be having a connection with each other, and they will be thus preventing or reducing the latency. Then the third one is the method that you can adopt when it is not possible to reduce the latency at all. So what can be done? Instead of reducing the latency, you can just allocate the processor to execute some other process which is ready with its data and everything. So such kind of processors are called multiple context processor, which means you are going to interleave the context, interleave the executions, so that you can efficiently utilize the processor. So the first one is prefetching technique. As I said, it is aimed to reduce the latency. So this is reducing the latency by bringing the instructions or data closer to the processor before they are actually needed. That is why it is called prefetching. So if you know that a particular instruction is to be executed in the near future, you are going to fetch the instruction. Along with the instruction, you will get the required data also. So that is prefetched even well in advance, before the user is before the processor is actually in need of it. So that is called prefetching. Okay, so it uses the knowledge of the expected misses in the program. So you have to understand that at this particular point there may be a cache miss. So instead of having the cache miss to happen, you are prefetching the data, and you are making sure that the data is available inside the cache. So that is prefetching. Okay, so there are two types of prefetching: hardware controlled prefetching and software controlled prefetching. Hardware controlled prefetching, you can have long cache lines, and you can even use the method of instruction look ahead. So long cache line means you will have something called the problem of fault sharing, because you will be having the caches being overlapped to each other. So there are chances that the data which is being used by one particular instruction falls in the cache of the other processor, which means the other processor is also having an access to this particular data. Okay, so that is the problem of false sharing. It is not actually sharing it, but since the data is being prefetched and stored into this longer cache line, what happens is the longer cache line will be accessed by multiple processors. So it may result in a false sharing, or some other processor is getting an access, or some other processor is also knowing about the instruction or the data that has been available. So that is called false sharing. It is not an original sharing being happening. It is just that there is a there is a there is a problem that this is being accessed, or this is available for some other processor. The second method is just like we know before, the instruction look ahead, and that is also a hardware based thing, which is you have to employ instruction buffers or some mechanisms like translation look aside buffers, which you can actually make use of for looking ahead of the instructions and planning the order of execution accordingly. So when you talk about this instruction look ahead, that can be limited because of the branches, which means if your branch prediction accuracy is not up to the mark, then you may have to face a poor performance. And also the bottleneck may occur as the buffer size cannot exceed beyond a limit. So these are some problems associated with hardware controlled prefetching. Moving on to software controlled prefetching. So this is the software controlled prefetching, where you will make use of a special kind of instruction called the prefetch instruction, which is actually given, or the instruction that is being called to get the data which is known to be removed, which means you already know that the data is removed, so you make use of the prefetch instruction to get the data. So this will be kind of a selective approach, which means you have to pre-decide on which are the data that is remotely available, which are the data that is locally available. So only when you have to deal with the remote access data, you will have to perform this prefetch instruction. You will have to make a call to prefetch instruction, and the prefetch instruction along with this remote data will be executed. So this will be kind of a selective approach. So what is the disadvantage? Because you have to make use of an extra instruction, so that results in an extra instruction overhead. And also the normal operating system will not support such kind of an instruction, so you will have to use a sophisticated intervention of a software. So these are the disadvantages of software controlled prefetching. The second method is about the coherent caches. But before that, we have to know what is the issue of coherence in prefetching. So when we are doing a prefetching, we have to make decisions regarding what should be done. So which means if you are going to update a particular block after it is actually prefetched into memory, that is if a particular memory location X is actually prefetched as a data for an upcoming instruction and it is taken to the cache, but later at a point of time before this particular instruction or was executed, if the memory location X is being modified, then that will result in a problem of inconsistency. So there is such kind of an issue while we are actually prefetching the data. So this is known as issue of coherence in prefetching. So this kind of an inconsistency problem may occur when you are actually prefetching the data for enabling or for reducing the latency. So to address these issues of coherence, you can actually have two approaches of binding, which is called binding prefetching and non-binding prefetching, which means you are going to take a particular data and you announce that this particular data or that memory location should stay binded or should stay unchanged until the execution of that particular instruction is being done. So that kind of an approach is called binding prefetching, which means you are collecting the data to the cache and also you make sure that that particular memory location will not be updated until the execution is complete. The second one is not giving any such guarantee, and that is called non-binding prefetching. So that is about prefetching and the probable issues that may occur when you are actually going for a prefetching technique to reduce the latency that may occur in the execution of instructions. Moving further, you have the binding prefetching, and this is the explanation for binding prefetching and non-binding prefetching. So as I said, the fetch is assumed to have happened when the prefetch instruction is issued, and it is the responsibility of the fetching process to ensure that no other process will update the prefetched value before it is actually used. So this is actually making sure that this particular data which is being prefetched is a critical section data. So it will be kind of making use of a locking mechanism. So the data stays locked or the memory location stays locked until the execution of instruction has been complete. Non-binding means it will it will not give such a guarantee, but rather it will invalidate a prefetched value when it is updated prior to its use. Which means just like we have the cache invalidate policy, we are going to check whether the data is being updated inside the original memory location. So if the data is being updated, what you have to do? You have to invalidate the copy of data that you have in the cache. So that is non-binding prefetching. It is not giving a guarantee that the data stays intact in the original memory address. There are chances that the data may be updated. So if the data gets updated, you will have to invalidate your content, and that is the policy which is available in the non-binding prefetch policy. So what are the benefits of having prefetching? As I said before, the latency can be significantly reduced and thus you can improve the performance. And prefetching the cache block line directly with the ownership will reduce the write latencies as well as also significantly reduce the network traffic. So then we can stop our discussion on prefetch techniques. We have discussed about hardware prefetching, software prefetching, issues with prefetching, then what are the approaches that you can use for avoiding such issues, which is binding prefetching and non-binding prefetching. And we have also discussed about some of the benefits of prefetching technique. Moving to the second one, which is using the coherent caching technique. So here, in the case of about the second technique, which is using the coherent caching mechanisms, we have learned about cache coherence preservation using Snoopy bus protocol, directly based protocol, and so on. So the same approach is being used in this mechanism also. So we are, if the underlying network is a bus based system, then we'll go for the Snoopy bus based cache coherence mechanism, which uses write update, write invalidate, Goodman's write once protocol, etc. Then if it is a network based system, we'll go for directory based protocol, where it is maintained using full map directory, such kind of mechanisms. So that is about the coherent caching techniques that we have adopted for reducing the latency. Now, um, about the benefits of caching this approach, as we know, this will reduce the latency. So by reducing the latency, you can improve the performance. Then the number of cycles being wasted can be significantly reduced, because we are having a cache coherence, which means you can reduce the number of read misses, so the number of cycles wasted can also be significantly reduced. Then up to a certain extent, it's not very accurate, but still up to a certain extent you can reduce the cycles which are wasted because of a write miss also. So these are the benefits of having the coherent caching techniques. So we have discussed about two approaches latency hiding. First one is prefetching, and the second one is cache coherent technique. So in prefetching and cache coherence, we are trying to reduce the latency. Whereas now we are going to see the third approach, which is the multiple context processor, where you are not actually trying to reduce the latency, rather you are trying to hide the latency, which means if there is a latency between the execution of a particular instruction, you are going to change the context of execution. You are giving the chance for some other instruction to execute, so that the processor will not stay idle. So that is the idea behind multiple context processor. So its aim is to hide the latency, not to reduce the latency. So let's discuss about multiple context processor. So as we know, in the case of a single threaded processor, one process will be executing, the other processes will be given a chance only after this particular process, that we all know. But when we talk about a multi-threaded processor, you can have a multiple context, and you can have context switching. We know how context switching is done. We have policies for that. So based on priority, or based on the need of the time, you will be changing the context. So the context which is suspended will be preserved somewhere, and the context which is given the chance will complete its execution. Then the suspended process will be given a chance to resume the execution. So we know that. So a multi-threaded processor can be used to suspend the current context and to switch to the another context. And such kind of a processor, a processor having such kind of an ability, is called a multiple context processor. So for a fixed number of cycles, you can make the processor busy doing some work, so that the number of cycles where the processor remains idle can be significantly reduced. Then even if you have remote reference, you will have to waste some cycle, of course. But if you can properly schedule the instructions, then you can, if you can properly perform context switching between the instructions, then you can also hide this wastage of cycles. Then the processor will be idle only if all the contexts are blocked. So that is the advantage of multiple context processor. So talking about the context switching, the same thing we have to discuss in detail later. But still, for now, we'll be discussing about what is the objective of context switching. As I said, the main role is to hide the latency, which means you have to make use of the processor, or make maximum utilization of the processor cycles. So you have to maximize the fraction of time that the processor is busy, or you can say in other words, you have to minimize the idle time of the processor. Okay, so you are going to maximize the busy cycles of the processor. So you can take the efficiency as the number of cycles the processor is actually busy divided by the total number of cycles taken for execution, which may have busy cycles required for switching the context, as well as the cycles which were kept idle. So that is the total number of cycles, and this fraction will give you the efficiency of the multiple context processor. So the basic idea of multi-threaded machine is to interleave the execution of several contexts in order to reduce the value of idle time without increasing the magnitude of switching. So you cannot spend a lot of time switching. So you cannot say that every 2 cycles the context keep on switching. That is not a kind of efficient processor. What you do is that you reduce the magnitude of switching. Still you can have maximum utilization of CPU or reduce the number of idle cycles of the CPU. Then that is a perfect multi-threaded processor, and this is the whole idea behind multi-threading. Now we have to talk about some states of context cycle. This will be discussed in detail later, but still we can just go through it. So there are basically 4 states for a particular context. First state is the context is ready for execution, but it is not given a chance to execute. So that is the ready state. In the next state, the processes or the context is under execution. Okay, so why I take the term context is because the task that is being done may be of a whole process or it may be of a sub process. So we can refer to both of them as a context. Okay, so when you say a context is ready, it is having all the necessary data and it is just in need of the CPU time. So that is ready. Okay, then we talk about running. So in the case of running state, the context or the process or the thread is actually under execution. Then leaving, it has completed its execution. Now we can take it out of the memory. That is in the leaving state. And finally block state, it was in need of something. It was need of some operands or some resources. So it cannot proceed further. That kind of a stage, you will have to suspend the execution and the process or the context will be taken to a blocked state. So that is various states of the context cycle. Now we'll see some of the issues that are actually there while you are talking about multi-threading, and some of the solutions that you can look for while having this multi-threading multi-threading under the view. So multi-threading issues and solutions. So multi-threading, as I said, there will be multiple threads of the same process or multiple process under execution or looking for execution at the same time. So you will have to efficiently manage these contexts, and you will have to perform context switching. You will have to make use of the efficient utilization of the CPU. So all these are actually a big task. Okay, so the architecture environment, when we talk about the architecture environment, there will be multi-threaded system. There will be a network of processors. It will not be just one single processor. Normally you will have a network of processors. Then along with the processor, there will be many memory modules. Okay, so every processor element is known as P, every memory module is called as M. Then usually will not have a global address space. Rather, we'll distribute the address space into too many parts and it will be distributed across the processors. So it is kind of a distributed memory architecture, not a global architecture. So there is a pictorial representation. So this is the multi-threaded model which was actually proposed by Rafael Saavedra in 1992. This was kind of the first architecture proposed for a multi-threaded processor. So you can see there is something called a context select. So what is its job? Definitely it will be to select one from the available context. So that is context select. You have got many registers, so it will be like a some register windows available. So they are there. There are some contexts available. So each one of them will be having a program counter which shows the instruction or the address of the next instruction. Then there will be some specific words available. So all of them are context. They will be stored in registers. The data will be stored in registers, and the context select is responsible to pick one out of all these available contexts. Then there will be usually one thread per context. If you are, even if you have one big process as a context, that is also fine. Okay, so it will be always one single process per context or one single thread per context. You cannot have two threads from the same context. It will not be considered as a context. Okay, if you can subdivide the process into many single tasks, then each one of them will be having a single thread, or if the process is not breakable, then that one will be taken as a single context. Then you have ALU, then the local references and the remote references, all these. So this is the proposed model for multi-threaded architecture. Now this is the environment. As you can see, there are loads of processors and memory modules. They are kind of interconnected with each other. So there is an interconnect available for interconnecting between them. So the processor, each of them will be having a local memory as well as remote memory. So if the memory is local to the processor, it will not take much of a time. But if it is actually a remote reference, then there are chances of latency, which means the request has gone to the memory and the response comes back to the processor. That time taken can be referred as latency. Okay, so the rate of request will be normally as 1 divided by R. So this is actually also proposed in continuation with the same model. This is also proposed by Rafael Saavedra. So this is an example of a three-thread processor, which means it can have a maximum of 3 threads at the same time. So this was proposed by H. Hirata et al. In a conference which was again conducted in 1992. So this is just an example model and an example design. So here you can see this corresponds to one single thread. This whole rectangle that you can see corresponds to one single thread. So how many threads are there? 3 threads are there. So you have to make 3 separate units. Thread 1, thread 2, thread 3. Then there you have an instruction fetch unit. There is an instruction cache. The instructions are taken from the instruction cache by the instruction fetch unit, and from that you will create threads. Okay, so there will be a thread slot available, program counter available, then a decode unit and an instruction queue unit. Okay, so what you see in this big rectangle, it is actually a thread slot, and inside a thread slot you will have a individual program counter, instruction queue unit as well as decode unit. So there are 3 thread slots available here because this is a 3-thread processor example. Then you can have some standby stations, or what we say the reservation stations. Then you can have instruction schedule unit. You can see there is integer ALU, barrel shifter, integer multiplier, FP adder, which is floating point adder, floating point multiplier, floating point converter, load store unit, then load store, multiple units of load store. Then you can have some banks which is actually used as a register. Okay, so the register set 1, register set 2, so and so. This is kind of a bank of registers. Then you will have some queue registers also. Put together, this is the model or the architecture of a 3-thread capable processor. Okay. So that is about multi-threading issues and solutions. This is just an example of multi-threading. Now about the issue. When you talk about the multi-threading issue, there is a problem called problem of asynchrony. So we'll be discussing about that. But before that, we have to know about some of the parameters that we have while we are going to analyze the performance. So since we are going to talk about multiple threads executing, we will have to talk about efficiency, we'll have to talk about context switching, we'll have to talk about latency. So there are some parameters which can be used to analyze the performance. First one is latency, which is the communication latency between a remote memory access, which means a processor is going to access a data which is part of another processor. So it will have to send a request, then that processor will have to send back a response. So that takes time, and that is known as latency. So latency may be affected because of network delay, cache miss penalty, and also the delay that may be occurring because of split transactions. Okay, contentions of split transactions, which means there will be multiple transactions happening in the same time. So when that results in a contention, that will eventually result in a delay. So that is about latency. Talking about the number of threads, there are, as the number of threads increases, the performance is found to have a slight degradation. So when you talk about the number of threads, there is a maximum limit of in the number of threads which can be interleaved, and that is it. So as I said, a thread can be represented as one single context, and a context will have a program counter, register set, which is used to contain all the data associated with the context, and also the status words, which says whether it is in running state or ready state, whatever it is, that status word, it is also available inside the context. Now, the third thing, you have multiple contexts, so there should be overhead in switching the context. So that is the context switching overhead, which is the number of cycles you have to lose while you are switching the context from the current to something else. So that will depend upon the switching mechanism and the amount of processor states devoted to maintain the active threads. So putting it all together, that is told as the context switching overhead. Last one is interval between the switches, which is the cycles between the switches triggered by remote reference. So whenever you have a remote reference, you are going to switch the context unless the reference is unavailable. So you are going to switch the context. So that switching the context may result in some cycles, and that is known as the interval between the switches. It is referred to as R. So when you talk about R as the interval between the switches, 1 by R can be taken as the rate of request for remote access. Rate of request for remote access. Okay. So this will reflect the combination of how the program is made, the behavior of the program, and how the memory system has been designed. All these will be having a role in deciding the interval between the switches. So all these are the parameters that you can use to analyze the performance of a multiple context processor. Now moving to the next topic, which is problems of asynchrony. So talking about the problem of asynchrony or asynchronous, you will have to talk about what is the problem and why is it significant. So this problem is actually found commonly in parallel processors. So as we know, parallel processor is a processor which is capable to execute something in parallel. Okay, so it can be a single processor which is capable to execute many subtasks, or it can be multiple processors which are going to handle multiple processes at the same time without intervening each other. So this parallel processor is not guaranteed to execute in a synchronous fashion. They will be executing in an asynchronous fashion, right? And they will be connected together using a network. So there are two problems that may arise when you have such a scenario. One is you may have remote loads happening, which is a load instruction that has to happen from a remote memory, that is called remote load. Second one is synchronizing the load operation. Whether it is a remote load or a local load, you will have to synchronize them. So these are the two problems associated while you are talking about a parallel processing environment. Now, what are the solutions that you can offer? There are two solutions that are being offered. First one is multi-threading solution. Second one is distributed caching solution. So, first we have to discuss about what are the problems, which is what is the problem with remote load and what is the problem with synchronizing the load. Then we'll discuss about the solutions offered, which is the multi-threading solution as well as distributed caching. So, let's start with remote loads. So talking about remote loads, we have to taken an example, which is you have a variable A and another variable B, which are located in two nodes. A is located in N2, B is located in N3. Okay, so A is located in N2, B is located in N3. Now what you have to do? You have to take them to a single variable C. Okay, so C is going to compute A minus B. So you have to take the value of A, you have to take the value of B to this particular location or that node where C is being created or C is being assigned. Okay, so C is assigned to some other node, you have to take the value of A, you have to take the value of B. But it is not part of the original node, which means A has to be remotely loaded, B also has to be remotely loaded. So there are two remote loads that is possible. So you have to perform two remote loads, then you have to subtract the data, then you have to store the value. So this is what happens. Okay. So you call the remote load as R load, then PA and PB be the pointers to A and B. Then C text is the context of computation on the node N1, where N1 is the node where C is located. So remote loads keep the node N1 idle until it receives the variable A and B from N2 and N3. As we know, when we have discussed about the pipeline, we have seen that the pipeline has to stall until the operands are available. Just like that, when you are going to have a node N1 which is going to get two remote data from N2 and N3. So what happens? Until you reach or until you successfully load the content of N1 and the content of N2 to, load the content of N2 and N3 to N1, N1 will have to wait, okay, or it will have to remain idle. And this uh, idle behavior of N1 can be counted as a latency. So the latency which is caused by remote load depends on the architectural property, which means if N1 is closely in association with N2 and N3, which means they are having a relatively lesser distance between them, then you will not have to spend much time. But what if it is located somewhere too far from the node N1? Then you will have to spend a significant amount of time to get the data back from N2 and N3 and load them to N1. This is the problem of, or this is the latency that is caused due to remote load. Until you get the data, you cannot proceed with the subtraction and N1 have to remain idle. So this is the latency that occurs due to remote load, or you can say the problem number 1. So there is a pictorial representation of the same that you can see here. So this is node 1. It has got a context, then it has got its own variables, registers, so and so. So this is the thread slot of node N1. Then you can see there is a node N2, there is a node N3. So N2 is having A, N3 is having B. So C is looking for A minus B. So what you have to do, you have to send a request to N2, you have to send a request to N3 for accessing the data. Now, these N2 and N3, they are not synchronous. They are not synchronously offered with N1. So they will be responding to the request at their time of convenience, and until then this node has to wait. Okay, and that results in a latency. So when A is ready, it will send a ready signal back to N1. Similarly, when B is ready, it will send a signal back to back to N1, but not necessary that this will happen at the same time. Okay, when N2 is ready, it will send the signal back to N1 and it will send the data back to uh, N1. Similarly, when N3 is ready, it will send the signal back to N1 and also initiate a transaction or a load from N3 to N1. Okay, so the content of A will be stored in this register, the content of B will be stored in this register, not necessarily in the same time. So this is the problem of the asynchrony, which actually can happen because of this problem. Okay, so this is about the problem of asynchrony due to remote load. This is talking about the synchronizing load problem, where you have to make sure that both the loads will happen at the same time. Okay, so that is about synchronous load, which we will discuss in the next slide. So you can see this is about the synchronizing load, where so as I said, they are computer, or the content of A and the content of B have been requested at the same time, but it is not sure, we are not sure that they will be receiving at the same time. Okay, because they are not synchronous to each other. So it is not sure that when will we get the data which is requested. So the ready signal may reach the node N1 asynchronously, which means the ready signal from N2 and the ready signal from N3 may reach N1 at different times. Okay, and then what happens is you have a particular type of waiting which is called busy waiting, which means the processor will have to check again and again whether A and B are both available. So this will result in a problem. This will result in an extra latency, and that is mentioned about synchronizing the load. If you cannot synchronize the load, if you cannot ensure that both the nodes are responding at the same time, the processor will have to wait and it will have to repeatedly check again and again whether A is available, whether B is available, whether both of them are available, can we start with the computation. All that the process will have to repeatedly check, and this will result in a latency, and that is the issue with the second part, which is synchronizing the load. So the latency caused by the synchronization load will be depending on how the scheduling has been done and the time taken to compute A minus B. Okay, so that is about synchronizing the load. So this is the two issue that we have noticed in the case of multi-threading, which is the problem of asynchrony, the remote load problem, as well as synchronizing the load problem. Now let's propose about the solution. So the first solution proposed was multi-threading. So multi-threading, as we know, the solution is to multiplex among many threads, which means when one thread is issuing a remote load request, the processor understand that this is a remote load, it may take time, so I can switch to another thread. So that is the solution which is told by the multi-threading type, which means when one thread is issuing a remote load request, the processor begins to work on another thread and so on. The cost of the thread switching is smaller to the latency of remote load. So what we have observed is that instead of making the processor wait until C is ready with A and B, you can have some other process in between, so that the processor will not feel or the processor will not have idle cycles. You can efficiently switch the thread without compared to the latency involved, the switching time will be very short. So you can actually go for thread switching. Then what are the concerns while you are having this approach? First thing is that the remote response will not be efficient, which means it will not come in the same time. You cannot promise that it will come in the same time. The process will have to significantly check again and again whether the process is ready, whether A is available, whether B is available, can we start with the computation. So that we have to check again and again. Okay, so the response of remote load may not return in the proper order. So what happens is that the process will execute another thread. By that time, this order may be different, and there is a chance of losing the idea or losing the sequence of execution. That is, after issuing a remote load from thread T1, we switch to T2, which also is making a remote load. So what happens is, in the end, there will be a confusion about synchronizing all these remote accesses. Then the second one is that responses may not return the same order because requests may be traveling from different distances. That is, a node 3 may be located very far from the node 1, or node 2 is located too close to N1. So node 2 may be responding very fast, whereas node 3 will be responding in a less slow pace. So all these may be affecting. So since the processor is having multiple requests at the same time, which means whenever you have a remote load, the processor is going to switch the context or switch the thread. So there may be chances that multiple remote load instructions may be given, and this will result in an increased congestion in the network, which will also add to the latency. So that is also possible. Now there is another problem, which means the load of the destination node may differ greatly, which means what if we are giving a request to node 2. Okay, you are asking for a remote load at node 2, but node 2 is actually busy doing some local transaction. So what happens? There will be an extra load which is given to N2. So that will also add to a delay in response, and that is called that is also adding to latency. So there are many reasons for latency, which is first is because of the distance between the nodes, or because of the congestion that may occur in the traffic, the congestion that may occur in the network because of the traffic, then because of the load of the destination node, which is the destination node is actually doing some other work and you are asking for another work to be done, which may result in a delayed response. So all these add to latency. Okay, so even if you can have a multi-threaded solution, there are chances that there may be some concerns with having this approach. Okay, so I have a pictorial representation for this. You can see that. So this is it. All these curly lines that you see are actually threads or subtask. Okay, so you have a node n1. So first context, second context, third context, it is there. Now what happens? N2 is actually, so here you had to get something from N2. So it is being asked. So N2 is requesting, N2 is being requested for sending the data which is available at A. So what happens? It will receive the response, it receive the request and it will respond at a time which is convenient to itself. So once that request has been made, you can see in node 1 the processor is going for another context which is again requesting for some other thread to execute. Then there may be a remote load, then the context again changes. So when node n2 is ready with something, it will send it back to n1 and only after that this particular context can resume the execution. So that may be having an increased latency. So what can be the solution for the concern that we have observed? First thing is that make sure the messages carry continuations, which means when you have a load to happen, you should be very clear on where to resume the execution. So that is the first thing. You should have to make sure that the messages carry continuations. Each remote load and response is associated with an identifier for the appropriate thread. So you should have an identifier which identifies which remote load is concerned with which process or which thread. So there should be an identifier. Then the thread identifiers are referred to as continuations of the message. So you have to make sure that there are identifiers for each of the load and these identifiers are going to work as the continuations of the messages. Okay, just like we have sequence numbers for packets, you have to make sure that there are identifiers for each of the remote load so that you can know where to continue with the execution. So these are some of the solutions that you can propose. The second solution that was given was distributed caching. So distributed caching, as the name says, you have to distribute the caches between the nodes. So this is kind of trying to solve the remote load problem. So every memory location will have someone called an owner node or the node which actually owns the location. So in this example, you can see N1 is owning the location B, N2 is owning the location A. So this is N1, N2. Okay. And what happens is you have to maintain a directory which contain import and export list. So based on, so that every node is having its own directory. So you can see what is the status of A, whether it is imported, whether it is shared with someone else, whether B is imported, whether B is exported, is it exclusive to someone or it is shared with someone. All these details are stored inside the directory. So you know whether it is shared or exclusive. Shared means multiple caches are having copy and exclusive means it is locally available. So if you are asked for a locally available copy, then you can easily share it with someone else. But when you have to share something which is actually shared with multiple caches, you will have to either update all the cache elements or you will have to invalidate all the other cache copies. Okay, so this is the idea of distributed caching. This was trying to solve the remote load problem. And this is a pictorial representation. So the only idea is that there will be someone called the owner node. The owner node will maintain a directory which contains the status of each of the variable that is associated with the node or the memory location that is associated with the node, and then you will have to decide on how to give access to the request. It can be either just a simple sharing if it is exclusively available, or if it is already shared, you have to make use of some cache coherence scheme also. So this is about distributed caching, which was proposed as a solution for the problem of asynchrony. So for today, I'll stop right here. So you can go through the lecture, understand, make your notes, and you can learn for yourself. Thank you.